Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 21st lecture of VLSI Interconnects course. Today we will be looking at equivalent circuit to simulate skin effect. In the previous lecture we discussed the concept of skin depth. We saw that we can effectively model the flowing current as एक मिनट ये शुरू से करते हैं ना, गड़बड़ हो गया. Hello everyone, welcome to the 21st lecture of VLSI Interconnects course. Today we will be discussing equivalent circuit to simulate skin effect. In the previous lecture we discussed the concept of skin depth. We saw that there is a effective area below the surface of your conductor which is available for conduction, and from that we could easily derive what is called the effective resistance when there is skin depth. In this lecture we will first start with skin effect in cylinder, and then we will take the cylindrical cross sectional wire and see how we can represent the skin effect with an equivalent RL circuit which will enable us to simulate the skin effect. So, the second topic will form the main part of today's lecture. So, let us get started. So, in the previous lecture when we ended, we saw a cross sectional wire like this with a square section, and there we said that effectively I can say that only this section, this part is available for me to conduct. However, we made sort of hand waving extension from a semi infinite plane to this region. So, in this lecture we will take a more symmetric geometry of a cylinder. So, we will take a cylinder which is conducting, it has a conductivity of sigma, and the current is flowing in this direction. So, your current is flowing in this direction. For this we will be looking at what would be the expression for the current in a wire like this. So, here again all the equations would start from the basic Maxwell's equation. So, we had a relationship of curl of E was equal to minus j omega mu h, and then in this conductor we had the relationship of j is equal to sigma E. So, if I substitute this in here, finally I will be getting these two equations. So, equation 1 and 2 would be my starting equation. Since we are interested in the current profile, we would be eliminating H from both these equations. To do that, what we will do, we will take a curl on both sides, right, and then we will substitute this expression from here. So, if I write it like this, if I take the curl of equation 1, I will get this equation 3, and in this equation 3, if I substitute from equation 2, so substituting from equation 2, I can get an expression finally of this form, right. So, what I will be having is this curl of j would be equal to minus j omega mu sigma j. So, this is the equation that we need to solve. This equation is irrespective of the coordinate system. So, whether we take Cartesian coordinate system, spherical or cylindrical, this equation would be valid. This can be further simplified using vector identities. So, I can write this curl of this operation, I can replace this as curl of this into, suppose this was a vector A, some vector A minus this term. So, if I just do that, I will get this expression. Now, here this part here we need to investigate. So, what is this? This is divergence of current. So, this is basically there is at one point what will be the divergence of your current. Now, it turns out that the divergence of this current would be because based on the continuity of charge, this will be related to the charge density as this. So, this rho is not resistivity, this is there is a subscript q here, this is the charge density. So, in a conductor like this, there is no source of charge. So, the charge density is not changing. So, therefore, this quantity is 0 and therefore, this entire term can be written as 0. Then effectively what we have is only these two terms. I can write these here. So, this is my final differential equation that I need to solve. Now, this will be true for all the components of J. So, Jx, Jy, Jz. However, in our geometry we had taken that the current is flowing only along the z direction. So, my J is, so we had taken that J is, no, I think here this was Z hat. So, therefore, I can now write it like this. Here again this part is my gamma square. So, similar to the previous analysis, I am now having an equation like this. So, in the first lecture on skin effect, we were essentially solving this equation in the Cartesian coordinates for a oversimplified case of a half space of conductor. In this scenario, there is a cylindrical symmetry. So, we will be solving this equation in the cylindrical coordinates. So, in the cylindrical coordinates, this will be your equation. We will also assume cylindrical symmetry. So, we will assume so in this case this is 0. So, variation with phi. So, what is your phi? Phi is this angle. So, there is no variation with respect to phi. So, we will assume this. So, if we solve it, we get very complicated equations which are essentially Bessel's functions. But we will not go into that much detail. So, we will look at the final expressions after applying the limiting conditions on the Bessel's functions. So, here also we can define a skin depth like this. So, this is your, you will get a constant like this also in this case also. Then there is case 1 when A is much smaller than delta. In that case, if you apply the limits on the Bessel's functions, the expression in form of Bessel's functions you will get a expression like this. So, here what you have is the cross section is something like this, right. So, your maximum radius is A and R is some point here. So, your J of Z is a function of R. So, your R is less than A, right. So, your R goes from 0 to A, right. So, for this you have an expression like this. Now, since A is much smaller than delta, in that case your R by delta would also be much smaller than 1, and therefore, these higher order terms you could neglect and your J Z of R you could write, which is approximately equal to 0. So, this is the case when skin effect is not present. So, this is the case when skin effect not significant. You can ignore the skin effect. Why? Because you are approximating this, getting this as J0. If you want a little bit of more accuracy, maybe if you neglect the term of r by delta to the power 4, you can still consider this term r by delta, and then you can notice that there is a j term here. Your current density will still be more or less constant, but still you can get a complex current. So, this will represent the inductive part of in this case. Now, we go to the other limiting case. In this other limiting case, A is much greater than delta. Delta was your skin depth. So, your A is much greater than skin depth. In that case, if you apply the limits and simplify the expression, you will get a nice expression like this. Here you can see that this looks familiar to you. Here if you replace A minus R by R prime, what you essentially have is J0 e to the power minus R prime by delta into e to the power J R prime by delta. So, you can see that here you can get this skin depth like this. The current density is attenuating below the surface of the conductor, and effectively you can say that this is my my conducting region, right. So, this so the analysis which we did for Cartesian coordinates with oversimplified cases, this is still valid. In a cylindrical case, we are getting closed form expressions for something like this. In a more practical scenario where you have a cross section of this form, you would more or less you will get this profile. To exactly solve for this this effect, you will require the full wave simulation, where you would be discretizing this geometry and then computing the current distribution on each of these elements, and then from here you will be able to find what will be the current distribution and then the effective resistance and also the inductance. So, that is all for this simple conductor, I mean the closed form expressions. Now, suppose we want to incorporate this skin effect in our SPICE simulations. So, in module 1 and module 2, towards the end we saw that we can capture the RC and RLC interconnects using lumped elements. So, we were able to simulate it using SPICE. Now, what we will do is that we will look at an equivalent circuit that will help us simulate the this skin effect from your circuits, equivalent circuits. So, we will be looking at this equivalent circuit model. This following discussion which I am going to present is taken up from a relatively very old paper. So, the paper is time domain skin effect model for transient analysis of lossy transmission lines. This paper is from 1982. It was published in Proceedings of IEEE. So, let us see what they did. The approach I will not be following exactly, but towards the end of this lecture I will be again showing plots from this paper and the schematics from this paper. So, again, what are our starting equations? These are our starting equations as usual. So, my first equation, this we have just now seen. Right now we are not taking any specific case of time, any time harmonic. So, that is why I have kept these equations in terms of derivative with respect to time. Now, what we have is these two equations which we will have to solve. So, right. So, to get inductance and skin effect, these two equations we are solving, right, for last 2 lectures. So, now what we will solve them in a slightly different way. What we will do is that we will again assume a cylindrical wire. So, there is a there is cylindrical symmetry here, and here I am showing the cross section. So, cross section of conductor. What we have done is we have now segmented this cross section into m rings. So, we have discretized, or we have segmented section into m m discrete rings, and then we are assuming that each of this ring would have a uniform current density. So, what would practically happen is that the current would uniformly current would continuously reduce below the surface of this conductor, right, but we are discretizing it. So, what we are saying is that there is a current density. So, this is the first ring. The first ring has the outer radius of r1, then this is the second ring, this has a radius of r2. So, your r2 is less than r1 as per our notation. The current on the first ring is J. So, the current here is J, is J1. Here the on second ring current is J2, and so on. So, we are assuming that the current density is constant on each ring. Inside this ring, the current density is not varying. The smaller our rings are, or more number of rings we have, more accurate will our analysis be. So, there will be there is a trade off between the complexity of this circuit and the accuracy that we have. So, we will assume that the current density on the ith ring is Ji, and area of the ith ring would be Ai, and then Ai I can write as, what will be Ai? So, what will be A1? A1 will be pi r1 square minus pi r2 square. So, that for the ith ring will be I square minus pi r plus 1, pi r I plus 1 square, right. So, this will be my Ai. Now, if I know what is Ji and Ai, I can also get the current density on each ring. So, the current flowing through the ith ring, what will be the current flowing through the ith ring? That will be II into II is equal to Ji into Ai, or I mean this we get from my Ji is related to, right. So, my current density is related to the current like this. Now, we take the this equation, right. So, let us take these equations one by one. So, let us take this equation first. So, if I take this equation, I can write it in the integral form like this, and then finally, I will have this closed line integral over h dot dl over 2 pi r. So, that will be equal to the area, I mean that will be equal to this total current. So, this will give you the total enclosed current. So, what I have is that I think I have a figure drawn here. So, I have rings like this, and my total, so my H phi, so the current is flowing in the z direction. So, I will have H phi only in this case. So, my H phi, if I have H phi at some R I that would consist of all the currents that are inside, right. So, for example, this will be total enclosed current. So, this will include all the currents here. How do I get that total current? I do a summation. So, I have a summation over the currents, which will give me this. So, my H I, so if I write my H phi of R I as H I. So, H I is in the phi direction. In that case, I will get my H I as this. Now, let us take the second equation which we had. So, let us take this equation. This equation we have managed to discretize, right. Now, we have to discretize this second equation. So, if we write this second equation here, so this is like in the vector equation. So, what I have is j is propagating in along the z direction only. So, I have z hat, and then this can be written like this. So, finally, that equation will be, second equation will be this. What I have to do is I have to discretize this equation now. So, what I have to do is I can, so this is a function of r. So, what I will have is j del r would be equal to del of h I del t, and what is h del by del t of h I, that is given by this, right. So, all the subsequent inner rings that should be considered in your current. So, for finite rings, what we will do is replace this differentiation by finite difference equation. So, my partial derivative with respect to r would be replaced by this difference equation. Once I do that, I can get an expression like this, right. So, I have replaced my differentiation with this here in this equation, right. I had this equation. In this equation, I have just replaced this, and this I have already got in terms of summation in from current. So, that I have. So, once I substitute that, I will get a expression of this form. Now, what I will do some rearrangement of terms. Here you can notice something, that this di by dt term is already coming in. So, di by dt with some inductance. So, you can see some inductive term is also cropping up now. What I will do is that I can write this, rearrange the term. So, here sigma I will take in the denominator, Ri minus 1 I will take in the numerator on the RHS. Once I do that, I get an equation like this. Here what is Ji? Ji is Ii by Ai, and Ji minus 1 is Ii minus 1 divided by capital Ai minus 1. So, if I substitute that, I will have an equation like this. So, Ii divided by sigma Ai minus I subscript I minus 1 divided by sigma Ai minus 1, and on the RHS you have this term in here. Now, if you notice this, so this is the what is this? This is sigma, this is conductivity, right. So, this is conductivity, let me write it here, yeah. So, this is and this is area. So, if I look at what is this dimensionally, A by 1 by sigma A. So, this you can see is the resistance per unit length, right, rho. So, this would be, yeah. So, it would be L divided by sigma A would be resistance of segment of L, and if I were to write a resistance per unit length, I would have 1 by sigma A, right. So, what you can say is that this term here, this term on this side is basically the resistive part, right. So, if I say let R I be the resistance per unit length of the ith ring, then I can replace this R I as 1 by sigma I, sorry 1 by sigma into A I, and once I do that I have this R I. So, I can replace this with R I. Similarly, what I can do is that I have this summation over here. So, I can replace this entire thing by L I. So, if I do that, I have a so on the whatever I had on the RHS term outside this summation, I am representing it by L I. This is inductive. So, finally, what I have is an equation of this form, which is this, and now you have sort of a KVL sort of equation where there is so this is voltage, there is some voltage balance here. So, here you can check this out. So, this is a very good equation which will help us make the equivalent circuit. So, for the innermost ring, what will I have is for the innermost ring, I will have this thing R m into I m minus R m minus 1 I m minus 1 is equal to minus. So, here the summation would be just the first only one current, right, because your K is equal to m. So, you have only one current, right. So, the summation is not there in this. So, this will be our starting point of like from where we will start building the circuit. Then from this I can collect the terms of this m. So, I can bring it on this side. So, my R m minus 1 into I m minus 1 is equal to this thing. In general, I can also get an relationship between R I minus 1 into I minus 1 in terms of the quantities for the ith ring. So, now I have a sort of iterative equation which gives me the relation between quantities in the I minus 1th ring and the ith ring, right. So, if I continue with this, I can make a circuit. So, let me explain how. So, let us take this equation. What does this equation say? This equation says that the voltage drop across the across the mth resistance plus the voltage drop across the mth inductance is equal to the voltage drop across the m minus 1th resistance when this current is flowing. So, the current is also not equal. So, if I want to look at this, it is something like this. So, if this is my R m and this is my L m, and my current flowing through this is I m, and current flowing through the just adjacent segment is I m minus 1, right. So, in that case what I will have is this. So, in that case basically this is m, this is m minus 1, my voltage drop across this part and this part. So, this part and this part is equal to the voltage drop only across R m minus 1. So, across R m minus 1, this is my drop. So, this is this voltage between this point, drop this point and this point and this point should be equal, or I can apply KVL in a loop like this. I can bring all these two on one side and that equal to 0, and from there also I will get the same thing. Now, similarly, I can proceed further. So, if the current is in this segment is I m minus 2, the resistance in this case would be R m minus 2, and this would be equal to. So, basically my what I have is I m minus 2 into R m minus 2 that is equal to this thing, right. So, I m minus 1 into R m minus 1 plus L m minus 1. So, this is L m minus 1 into the two currents I m plus I m minus 1 divided by dt, right. So, this is my thing. So, here I can go on doing that. So, this will be m minus 2, and similarly I can go on doing like this. This will be R 2, this will be L 2, and this will be R 1. So, this would be the outermost ring. In the outermost ring, if I look at the I just have this thing R 1, and this is my innermost ring. So, this is my innermost ring. So, this is my equivalent circuit. Now, if I know the material parameters like conductivity, permeability, etc., and also I have segmented it. So, I definitely know what are the these resistance these radiuses are. So, I can compute LIs, I can compute RIs from AIs, right. So, from this I can compute all these parameters, and then I can frame a circuit like this. So, these are the figures directly from the paper which I had referred to at the starting of this discussion. So, if I have a ring like this, this can be replaced by a circuit of this form, and this is the equivalent circuit. So, this is the entire equivalent circuit. So, this would then be included in the transmission line parameters. You can see this is like V of x and t, this is V of x plus delta x into t. So, this is delta x segment, a section of transmission line with skin effect losses. So, then the analysis which we had done can be extended, including this skin effect. So, this discussion, I mean this is one way of representing your skin effects. This is not an exhaustive discussion, there are multiple methods. For further reading, I would refer to you another paper from IEEE transactions on VLSI systems from 2004. The title is Modeling Skin and Proximity Effects with Reduced and Realizable RL Circuits. So, basically it tells that I mean furthermore, to incorporate skin effects and proximity effects in existing generic simulation tools such as SPICE, simple frequency independent lumped element circuit models are needed. So, these type of are needed. Here in this figure in this paper there is this interesting figure which shows that how would your response vary. So, this is for the case, this is your node voltage with respect to time. So, this is for the case when your R and L are constant, they are not function of frequency, but when skin effects trigger in, what you have is your R and L become a function of frequency. So, your R is a function of frequency and your inductance is also a function of frequency. So, in that case you have a signal like this, and this you can see the distortion introduced because of this R and L becoming function of frequency. So, we will stop here today. In this lecture we saw the skin effect in cylindrical conductors. We derived an equivalent circuit where we discretized the cross section to arrive at the equivalent circuit, the parameters of those equivalent circuit, and we saw that with those fixed values of R and L's, and if we make a ladder like circuit, we can incorporate this skin effect into our SPICE simulations as well. So, this method of discretization which we saw in this lecture is actually a precursor to the numerical extraction technique. So, when we numerically extract the effective resistance and inductance for interconnects, we do something very similar to this. So, in the next lecture we will start with power dissipation in interconnects, and we will discuss what are the main sources of power dissipation and how interconnects contribute to that. That is all for today. We will meet in the next lecture. Good day.